Okay, ladies and gentlemen, welcome to the third lecture of parallel algorithms. Are there any questions about the past lectures, about the assignments? No? Okay. Then, as you know, we had an exercise for this week about finding the first one in an array of 0 elements. I will discuss this exercise together with an explanation of, well, let's say, a possible generalization of the approach that we use to solve this exercise. And then we will discuss three remaining basic techniques, among them accelerated cascading, which is a technique to combine basically two algorithms in order to transform an algorithm that's not weakly optimal into a weakly optimal one. Then a discussion of pipelining, and finally a discussion of symmetry and break. And after that we are ready with the basic techniques, and we can concentrate on more involved techniques concerning the manipulation of series matrices. Yes?
Would that then be sufficient as a basis for the assignment?
No, it's not sufficient for the assignment. There is a part of assignments that also involves manipulating recurrences, and these recurrences will be discussed later on. Yeah. So, let's start with the following problem. That's called find a one index. You are given a Boolean array, and you have to find the first one, the position of the first one in that array, with an algorithm that will cost you constant time and will cost you an O n amount of work. Well, that seems to be very trivial, but consider this exercise, and please give me the index position of the first one in this array in constant time with an O n amount of work. Yeah. That's not that easy, and well, the solution is that here you will find the first one, and it is on index position 249. But how to come up with such a result in a constant time with a minimum amount of processes? That's the problem. Because, well, it is not that difficult to find an algorithm that takes more work. So that, for example, would cost you an n² amount of time when using a serial algorithm. We will try to use that algorithm only in a final phase. And here you encounter, well, let's say, the same argument as we used when composing this algorithm that could find a maximum with a very small number of processes. Yeah? So in the beginning, you can't often afford to use the best algorithm for your approach, because it takes too much work, and you have to do something in between before you can apply that final algorithm. Here we have the same case. We have an algorithm, first one, that can be used to solve the problem, but it takes O n² amount of work, while meeting the requirement of a constant time. Well, in order then to apply that algorithm, first one, you first have to ensure that your work can be reduced. So you have to pre-process your data. After pre-processing, the remaining amount of data you have to process can be made sufficient to ensure that the amount of work here is allowed. Well, in order to do so, we solve just a different problem. we solve a relaxed problem. So what we do is we try to solve the problem, is there a 1 in the array that we are searching for? That's a very easy one. So the algorithm someone answering that question only takes O(n) amount of work and O1 amount of time. We combine then the results of someone and process first one on the remaining data structure, collecting all the outcomes of someone. And with the help of a divide and conquer approach, we obtain a O(n)(O1) algorithm. That sounds a little bit mysterious, but well, let's first concentrate on this algorithm. First one that, well, is too costly for us to perform, but basically answers our question. And here again the idea is that, well, if you would compare for every I less than j, ai and aj, and you discover that ai and aj are both equal to 1, then you set aj to 0. That means if there is an index position, aj, that is not the first one in the array containing a 1, then aj loses and aj becomes 0. So after doing this operation for I less than j for all these pairs between 1 and n, you are ensured to have at most one index position containing a 1. Because as soon as there are more index positions having a 1, then n minus 1 of them will lose, because there is an index position before them containing a 1. If there is no 1, well, then of course the whole array stays what it was, containing only zeros. Now in the second phase, you assign first one position to n plus 1. Well, that's a default position. If your array will not contain a 1, then you will return first one pos unchanged, and that signs that your array only contains zeros. At the when on one n plus 1 position, there will occur a 1. So, meaning there is no 1 effectively in the Boolean array itself. And then, well, it's very simple to detect whether or not there exists a 1. If ai equals 1 for I between 1 and n, then you assign first one pos equal to I. And there is only, we have the guarantee, there is at most one index position containing a 1, so this position is uniquely defined. Okay, so by using this algorithm, we are able to solve the first one problem, but of course we have to take care for the total amount of work here, and that's very easy to see. Here you need at least an O(n) square amount of work, because you need to make a comparison between every I less than j between 1 and n. So here is the operation going on. After step 1, array A contains at most 1. So all these index positions now are changed into 0, except for this position, and it's easy to find this index position by the second statement. Okay. Analysis O1, O1, and O1 for the time, and O(n) square, O(n) and O1 for the amount of work, resulting in a total O1, O(n) square for the complexity profile of the algorithm. So basically we are able to solve this problem, but we can't comply to the requirement of only having O(n) amount of work. So what we would like to do is we would like to simplify this. We would like to study a more relaxed problem, and that problem is looking for only if there occurs a 1 in the array, and trying to combine that algorithm with the algorithm first. So let's study the problem of finding in a Boolean array an index k such that ak equals 1. Well, that's an almost trivial task. Here is the algorithm, sum1. Begin, set your output to 0. Yeah. For j between 1 and n, do if aj equals 1, then output 1 and return output. Here output 0 means there doesn't exist any 1 in the array, and else output here gives you the result. There is a 1. Yeah. Okay. How could you now use sum1 in order to apply first one in a less costly way? Well, the idea is as follows. This sum1 solves your problem partially. You know that there exists a 1, sum1 returns for this array 1, but you don't know where. But now suppose that initially you would apply sum1 to a subarray of your original array. So suppose you have k of those subarrays and you apply sum1 to them individually. Then for a subarray that does not contain a 1, you will return a 0. And for a subarray containing a 1, you will have returned a 1. That indicates where you can look in a more precise manner for the array containing the first 1. Yeah. So you apply sum1 to these subarrays, you receive a 0 or a 1. Then you have a combination of zeros and 1s telling you which subarrays contain a 1. You can apply first one to this result, so the results of the subarrays, to find the first subarray that contains a 1. If you know which subarray contains a first 1, then you can inspect that subarray. And you can apply your full computational power to apply first 1 to that subarray. So the idea now is we apply sum1 in parallel to the subarrays of A. Then we apply first 1 to these outcomes to locate the subarray of A containing the first 1. And then finally, once we have found in which subarray we can find the first 1, we apply first 1 to retrieve its exact location. And that combination will enable us to come up with a final solution. And so the idea is we distribute powers, but not too much, to find an approximate location for the first one. And once we have found the approximate location, we apply full computational power to search for locally for the first one. Okay, so here is the idea. If you have your array, then first divide it into subarrays. Here you have the subarrays. You apply sum1 to these subarrays. Now the result here is a 0, here a 1, here a 1, there a 1, 0, 1, 0. Applying first 1 to this resulting subarray gives you the number of the subarray containing the first 1. Yeah? Okay, so first 1 will indicate you will find your first 1 in subarray 2. Now you can concentrate completely to subarray 2 to apply first 1 to exactly find the first 1 here in that subarray. So here you find the first 1. And that leaves you of course, from computing in the whole array the first one. It's sufficient to find where approximately in the first phase your first one will be located. And then doing a search for the exact position. So, what will be the outcome here? The outcome will be a distributed first one algorithm. And this algorithm first divides the array A into the square root of n subarrays of length square root of n. And to these subarrays, someone will be in parallel to give you a 0 if the array doesn't contain a 1 and a 1 if it does. What's the amount of time? What's the amount of work? Well, applying someone in parallel will cost you O n amount of time. Someone has the complexity profile O n O1. So that means that O square n is the amount of work you need for applying someone to a subarray. You have square root of n subarrays, so the total amount of work is square root of n times square root of n is the O of n. So the first phase in total will cost you this amount of work and amount of time. Then we enter the second phase. So we store the results of applying someone in an array of size square root of n, where ci equals 1 if the ith subarray contains a 1. We found that with the help of some. Okay. Again, well, that will cost you O square root of n amount of work and O n amount of time. Then apply first one to this array. This array containing the square root of n entries. In order to find the first subarray containing. So, we can find here an index, and now, if you know the index position of the first array that will contain the first one, you can compute in a very exact way the subarray that you need to investigate in order to find your first one. And if first one returns m, then you know that a m minus 1 times square root of n plus 1 until m times square root of n is exactly the subarray, the index positions that will be delivered with the first one. Yes?
If you know the first subarray has a 1, then you don't have to look at the other subarrays, right?
Yeah, but you have to do it in parallel. You don't know.
Okay. Yeah,
You are quite uncertain where this first one is. Indeed, you can, of course, you could come up with special cases in which the algorithm does not need to perform all the work you have to do, but you never know. In worst case, you could be forced to do it. Okay, so this is the subarray we have to investigate that will contain the first one. The only thing we don't know is where in this subarray the first one will occur. But happily, we can apply first one to that array and return the result. And now first one, of course, investigating again an array of size square root of n, will return you this first position with, in constant time, with an amount of work O square n times O square n, and that's O n. Now, if you look here, what the total costs of the algorithms are, we have a constant number of steps. So here we are O1, 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 so that means O1 amount of time. Here we need O1, O n, O square root of n, O n, O n, so that means O n amount of work. And here again, you have an idea of how to use divide and conquer by using divide and conquer by applying first an algorithm that gives you an approximate answer to your problem in parallel, combining the answers, and then finding out where you have to apply the full power in order of your algorithm in order to come up with the final result. And so this is a general strategy. Be very careful in applying your computational powers. Often you can find it far more efficiently if you first try to find out where you have to apply this computational power effectively, and then apply it. Okay. Let me give you finally an example of application. That might be more convincing than a general story. So here I have a very simple array. I have an array of 9 elements. I divide my array in subarrays of size 3. I apply sum1. Sum1 is applied concurrently to these arrays. Now I assemble all the results into an array C containing 3 elements, and now I find my first one in this subarray C. Yeah? Applying find1 returns 2. That means I have to look in my second array. And more precisely, I have to come up with the index positions of the array A, where that I have to investigate in order to find my first one. Well, these index positions are 4 until 6, and the subarray is 0, 1, 0. Now I have to apply first 1 again to the subarray of size 3, and I come up with an index position of 2, and now I have to translate, of course, these index positions, and I find here, well, it is the second element of course, the second subarray, so that means that 3 elements are preceding this subarray, so the final index position is 5. Yeah? And that is the final result of the algorithm. So it sounds rather complicated, but you will see that many of these algorithms that apply a divide and conquer strategy will use this kind of idea. So first to distribute powers and coming up with approximate answers, and then use a part of the result to apply a full algorithm. Okay, here I have a problem that might be more interesting than finding a first one. And this is the following. Given an algorithm A of n elements, where I know that at every index position, this array is filled with elements containing an integer between 1 and 8. So we have a range restricted array. Now you have to come up with an algorithm to determine the minimum element in that array in O(n), O1 time. Now you know that we could find the maximum with an algorithm that will cost you an O(n) to the power 1 plus c amount of work and constant amount of time. Could you improve that once you know that your array is range restricted? Using the same technique as we applied before. So, well, give me your first guess. What would you do? Do you see a correspondence between this problem and the problem we just solved? Yes?
The minimum of the subarrays?
The minimum of the subarrays. Okay. That's you could do that. But there is maybe a more easy one. What's the correspondence between this problem and the problem we just solved? How could you use this information? AJ is between 1 and... How could you convert that information to make an array, a Boolean array, where finding the first one comes down to finding the minimum. Well, let me give you the answer. First you initialize a new array B. You ensure that at every position there occurs a 0. Then, at every position AI, you know that there is an integer between 1 and 8. So you fill B, Aj with a 1 for every j. Meaning that we now have a Boolean array indicating for each integer position whether or not it occurs in the original array A. So finding the first one, the index position of the first one, gives you directly the minimum of your original array A. Yeah? Because the first one means it is the lowest number that occurs in your original array A. Yeah? So finding the first one, by this divide and conquer approach, on the array B, gives you an index position, and this index position is the minimum of your original array. So here you see a very useful technique. That is, once you have an algorithm for a problem, and you have another problem, try to find out how you can reduce your new problem to your old problem in order to minimize your amount of work. And this, in fact, is a reduction. This is a reduction of a new problem, finding the minimum in an array, to a problem you already know. And that's also the reason why this finding the first one plays an enormous important role, because there are many problems that in this way you can reduce to finding the first one. So please be careful and try to come up with these reductions in order to minimize your efforts. Okay. So this ends our exercise, and now we have to come up with a new technique, accelerated cascading. And accelerated cascading has something of applying magic in parallel algorithms. Because what we have is, in general, two algorithms that, each possess a certain advantage and a certain disadvantage. So suppose that you have an algorithm that's fast but non-optimal. So time is okay, work is not okay. You have another algorithm that is, optimal, so it uses the right amount of work, but it is slower. And now you would like to come up with a technique to improve both aspects of your algorithm. So you would like to come up with a faster algorithm that is optimal, or weakly optimal, I should say. Yeah. So what I would like to discuss is a technique that you can use to turn non-optimal algorithms into optimal algorithms. Yeah. While improving, of course, the amount of parallel time in the heat. And to do that, we will discuss a particular case, and that's the very familiar algorithm for finding the maximum in an array. So we know from our discussions that there exists a O log n algorithm for finding the maximum in the balanced tree. Yeah. So of course we know that there is a faster CRCW, but if you are confined to a CR EW architecture, then that basically was the best we could do until now. This algorithm is optimal, but it might be that we are able to find a faster algorithm. Well, there is one, but this algorithm is non-optimal. So there is an algorithm that will cost you log n amount of time, but n times log n amount of work. So it's slightly off weekly optimum. So we would like to combine these two algorithms to come up with an algorithm that is optimal, so it will cost you n, but it is faster than this O log n. And that's the technique of accelerated cascading. We combine these two algorithms and ensure that we have an optimal, weekly optimal algorithm. The idea here is that we first concentrate on this very fast but non-optimal algorithm, and then we turn it into an optimal one. So the algorithm we would like to discuss uses a special data structure, and that's a doubly logarithmic tree. And this is a very easy generalization of binary trees. In binary trees, you have for every node at most 2 children. Here the number of children is much larger. So suppose that you have in total n is 2 to the power k leaves, and you have a tree built for that number of leaves. Then how this tree is defined in an inductive way? Well, if k equals 0, so then you have n equals 2, then a DLT2 tree is a tree with a root and 2 children. So that's a very simple one. And these are the leaves, these 2 children. Once k is larger than 0, then a DLTN tree is formed as follows. You take the root and you form square root of n children. And these square root of n children are the roots of a DLT square root of n tree. Yeah? So you have square root of n children. Each of these children is the root of a DLT square root of n tree. It's very easy to see that then in total we have k plus 1 levels, and the depth of the tree equals to k plus 1. And that's, of course, giving the name here. So if you have a doubly logarithmic tree, then you have to apply the log function twice to n to come up with the height of the tree. So the height of the tree equals log n plus 1. Let me give you an example. Here we have DLT2. Here we have a DLTN, and a DLTN consists of a root having square root of n children, and each of these children is the root of a DLT square root of n 3. Yeah? Very concrete example. Here a DLT16 tree, one root having 4 children. 4 is the square root of 16. Each of these is the root of a DLT4 tree, and a DLT4 tree has 2 children, and each of these children is the root of a DLT2 tree. And DLT2, of course, is the base case. Okay? Now note that 16 is 2 to the power 2 to the power 2, so the depth of the tree is equal to 3. Yeah. There is a simple computation for providing you the number of nodes, basically giving you an idea of how many nodes are there at each level. Well, it requires you some manipulation, of course, but that's quite easy, and we will take that for granted. What's more important is that we can find an algorithm for finding the maximum in a DLT entry. using a DLT entry. How to do that? Well, consider the n input values you have to consider, for example, assembled in an array, as the values of the leaves of a DLT entry. And then you traverse the DLT tree level by level, starting from the leaves. And at each level, for each node in parallel, you use this CRCW algorithm that we know. Yeah? And that gives you, on the children, that gives you the maximum in O1 amount of time using O(n) square amount of work. Yeah? And then you return the value computed by the root of this tree. Yeah? So basically at each level you process the children, you return the result into the root, and you go one level up. Yeah? Well, you can imagine that here Tn equals O log log n. That's not that difficult because all the processing level by level will cost you O1 for each level. Each level performs this CRCW PRAM algorithm to process the children and to return the result into the root. Well, how many iterations do you need? That is the number that is equal to the height of the tree, and the height of the tree is log log n. So the amount of work is O log log n. Now what's the amount of work? The amount of work is On for each level. At the lowest level we need an On amount of work. This amount of work is reduced, but you can prove that it is not improved essentially, and that again here the number of iterations you need, so the number of levels, will dominate. And in fact, the amount of work will require On times log log n. If you don't believe that, then simply give a look to the previous slides telling you what the amount of nodes is per level that you have to process. Add them up and you will come up with On times log log. So, the good news is we have a very fast algorithm. Now it costs you log log n instead of log n, but the amount of work is slightly increased. It's not the O of n, but the O of log log. So what we would like to do is to see whether we can improve it. Okay, here I have the basic idea behind this computation of Tn and Wn, but I think, well, that going through these computations will be an easy task that can be left to you at home, because it does not add to our understanding. What's more important is how we can find the algorithm that indeed reduces the number of time for the balanced tree method. So, okay, that was the idea. So now the result is the following. We have a balanced tree method that we started with, and now we have improved our algorithm by applying this DLT technique, but we discovered that now our algorithm is non-optimal. And what we would like to preserve the advantages of both algorithms. So we would like to come up with a faster algorithm than the balanced tree algorithm, but we would like to preserve optimality, because here we are losing it. And the idea now we apply is accelerated cascading. And here you have in fact something that resembles the idea we applied in to our first exercise. What we will do is we try to come up with an technique that, well, uses here what ensures weak optimality until you can afford your algorithm that will cost you more work. And so we see that, well, in obtaining your maximum, you can't apply this DLT algorithm from the start. This DLT algorithm will cost you n log n amount of work. So what's the solution? Try to reduce the information that you need to process until the amount of information you have to process is small enough to afford this amount of work without violating the bounds. So, what we are doing here is we look at the balanced tree method. And we know that in the balanced tree method, we also are processing elements and we are reducing information. Yeah? The amount of information we need. So, for example, at the base level, here we have the leaves. We combine them into the maximum of these two. Yeah? That effectively means that we reduce the amount of information we need to process to half of the original information in each level. So if we apply that for n divided by log n levels, or sorry, if we do that for log n levels, so here we process this information until we have processed log n levels, we come up with n divided to the 2 to the power log n, and that's log n. So what we have obtained here is a number of elements that's equal to n divided by log n. Yeah. Please remember that log n simply is 2 to the power log n. Yeah. And if you process k levels, then you will end up with n divided by 2 to the power k. Yeah. During, by the way of this halving procedure. So, after we have processed this, we have obtained a number of elements we have to find the maximum in that contains O n divided by log n elements. And once we have n divided by log n elements, we apply now the DLT technique. Because now m equals n divided by log n. Now note that the amount of work we need is m times log n. n times log n now is less than the O of n. Because, well, here, n divided by log n times log n is a number that's less than n. So, here we have log n levels, and now we have Tm equals log n, and that's smaller than or equal to log n. And the amount of work here is m times log n, that's m times, that's smaller than or equal to m times log n. M was already smaller than n, so this is less than, m is n divided by log n, so the result is 1. So, here the basic algorithm now is clear. What we have found here is an amount of time that is log n plus log n, that's equal to log n, and the amount of work is O n. Here is also O n, so the total amount of work is O n. Yeah? So the result now is an algorithm that preserves the fast time complexity profile of our DLT technique with the optimality technique of our balanced tree. So accelerated cascading, if it succeeds, that's not guaranteed that you can apply this trick to every algorithm. If it succeeds, guarantees you that you can preserve the advantages of box. So that's enough for this part. After the break, I will give you a general outline of this accelerated cascading problem, and we will present an exercise for a more general formulation of this problem that gives you enough stuff to